and that looks terrible. So let me arrange and zoom and fix. This is horrible. What can I do to make this appear reasonable? Certainly don't want to see the cabling. Well, crude. That's horrible, in fact. And it's out of focus. Let's add a little lighting. Well, okay, here we go. Aerospace Engineering Honors, April 15th, 2021. And this is going to be a debrief on homework 6, dealing with circular, elliptical, and Hoffman orbits. I'm going to work through the solutions to it right now during class time. It begins. A satellite orbits Tantalus 6 at a constant altitude of 428 kilometers above its surface. Tantalus 6 has a diameter of 10,900 kilometers and a mass of 8.06 times 10 to the 23rd power kilograms. Calculate the orbital period of the satellite and express your final answer in units of minutes. All right, well, this is supposed to be the easiest warm-up question I can give you because it's for a purely circular orbit. And by now, for purely circular orbits, wow, I guess the autofocus just is slow. For purely circular orbit, there's only two equations of interest to us. T squared equals 4 pi squared r cubed over gm, where r is the orbit radius in meters, t is the orbital period in seconds. V is equal to gm over r, where r is the orbital radius in meters. V is the speed of the spacecraft in orbit in meters per second. Great. Well, so we'll call this thing the key, huh? For number 1, you could do a little sketch. Now, if the diameter is 10,900 kilometers, that means the radius is 5,450 kilometers. Just divide 10,900 by 2, and you have the radius. The altitude is 428 kilometers. So the orbit radius is the sum of the radius of the planet, really I'll use capital R, the radius of the planet plus the altitude above the surface of the planet. And I didn't have any coffee this morning, so I'm just going to rely on my calculator, go 10,900 divided by 2. Good, I got that one right. Now add to that the orbital altitude of 428, enter, and it says the orbit radius is 5,878 kilometers. And I'm trying to have this where you can see it reasonably well. All right. Given the mass and the radius, calculate the orbital period. So t squared equals 4 pi squared r cubed over gm. And what I'm going to choose to do this time is everything on the right, then take the square root of it. So 4 pi squared, r is 5,878, but those are in kilometers. I need to convert it to meters by multiplying by 1,000 or adding 3 zeros. Now cube it. Divided by, whoops. Oh, this pesky little calculator. Boop. Divided by g, 6.672 times 10 to the negative 11th power, divided by the mass of the planet, 8.06 times 10 to the 23rd power kilograms. Boop. Great. So this huge number of seconds is t squared. Now I have to take the square root of that and get that as my answer. T equals 12,210 seconds. But it says here, please express it in units of minutes. There are 60 seconds in a minute. So divide by 60. And the answer is 204 minutes. So much for number one. Number two, a second satellite also orbits Tantalus 6. This second satellite is moving at an orbital speed of 2,120 meters per second in a circular orbit. Calculate its orbital radius. Well, there's only one equation that we are interested in, and that is for a circular orbit, the orbital speed is the square root of the universal gravitational constant g times the mass of the planet divided by the orbital radius in units of meters. So I could write v squared equals gm divided by r. And what I want to solve for is r, the orbit radius. That means these two terms swap. Or if you want to do it in two steps, multiply both sides by r, then divide both sides by v squared, and you have r is equal to g times m divided by v squared. All right, well, so g times 8.06 times 10 to the 23rd power, yep, confirmed, divided by 2,120 squared. Enter. Now there's the answer, but it's in units of meters. And although I didn't tell you to put it in units of meters, I think you're starting to recognize my style or habit is to put it in units of kilometers. So I'm going to divide this by 1,000. Boop. And there's my answer. To 3 sig figs, this is 12,000 kilometers. But you can't write it to 3 sig figs in this format. So what I could do is write 1.20 times 10 to the 4th power kilometers. And that makes it 3 sig figs. The 9 is going to round up. So this 119 rounds up to 120. All right, so there is the answer to number 2. If you left it in meters, that's fine. In meters, this is 1.20 times 10 to the 4, 5, 6, 7 meters. Okay, I'm not going to penalize you if you left it in meters. Number 3. Now think about this homework. Circular. We've just done 2 circular orbital problems. Number 3 is elliptical. An Orion spaceship is in an elliptical orbit around the asteroid 4 Vesta. That I picked because that's the one I found and photographed this past month or so. This asteroid has a mass of 2.59 times 10 to the 20th power kilograms and a diameter of 526 kilometers. If the Orion spacecraft is at a periapsis altitude of 70.0 kilometers above the surface of this asteroid and an apoapsis altitude of 4 to 25 kilometers above its surface, then calculate ABCD. Okay, so we're kind of forced to assume that the asteroid is spherical. It isn't in real life, but that's beyond what we can handle in this course. So periapsis of 70 kilometers. Let's see, what have we got here? We have a diameter of 526 kilometers. So half of that, of course, would be the radius of this asteroid. 526 divided by 2. Beep, 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 beep. Fortunately, I have a calculator working faster than my brain. So the radius of this asteroid is 263 kilometers. Periapsis altitude, measured from the surface, h of peri, is 70 kilometers. Apoapsis altitude is 425 kilometers. This is not a circular orbit. This is an elliptical orbit. So you're going to be using the properties of elliptical orbits. Here's the asteroid. Here's the periapsis distance. It's the smallest distance from the surface of the asteroid to the Orion spacecraft. On the opposite side is the apoapsis altitude, the distance from the surface of the asteroid to the Orion spacecraft when it's at its farthest point away from the asteroid. So asteroid 4 Vesta, Orion spacecraft in an elliptical orbit, periapsis altitude, apoapsis altitude, and if you look at this geometry, it's supposed to make it obvious to you, the periapsis radius is the radius of the asteroid plus the periapsis altitude. This plus this plus this equals that. The radius of the asteroid plus the apoapsis altitude is the apoapsis radius. If you add the periapsis radius to the apoapsis radius, you have the major axis. Half of the major axis is the semi-major axis, A. And if you want a formula, here it is. Semi-major axis is this average of the periapsis radius and the apoapsis radius. Great. So what am I going to do? I'm going to take the radius added to this, the radius added to that. Well, radius plus radius is diameter. So really, what I could do for part A is say 526 kilometers plus 70 kilometers plus 425 kilometers total is the major axis. If I then divide it by 2, that will be good for me and for you. So, open parentheses, 526, I hope is the, 526 plus 70 plus 425, close parentheses, divide by 2, enter. The semi-major axis, the answer to part A is 510.5. I'll leave it like that because I'm just going to use it in my calculator again anyways. Probably. So 510.5 kilometers is the semi-major axis, and that's the answer to part A. Part B, for the orbital period, it is the same equation that you use for circular orbits. In fact, that's why it's written here with an A. It says Newton's version of Kepler's third law says t squared equals 4 pi squared r cubed over gm. Well, for an elliptical orbit, the semi-major axis A is the average orbital radius. And that works for calculating average speed as well as orbital period. So I'm going to use t squared equals 4 pi squared a cubed divided by g divided by m. In this case, 4 pi squared. Now r is the semi-major axis. I need to turn it into meters. then cube it. Then I can divide this by universal gravitational constant. And finally, I can divide it by the mass of the asteroid, which is 2.59 times 10 to the 20th power kilograms. Okay, so this huge number is t squared. Now take the square root of it, and there is the orbital period in seconds. T equals 17,434 seconds. Too many sig figs. This is actually a reasonable number. I'm going to divide it by 60. 290 minutes, divide that by 60, less than 5 hours. Yeah, asteroids are so weak and small, their gravity is a small acceleration, so orbital periods are going to take a while. Part C, to find the periapsis velocity, we go to my handy dandy reference sheet that says, oh, the periapsis velocity, here it is. It says is 2 pi times the semi-major axis divided by the orbital period times the square root of the ratio of the apoapsis radius divided by the periapsis radius. I'm thinking these should probably be lowercase letters instead of capital R's, but oh well, too late. Now, circumference divided by period is average speed. So you could calculate the average speed, if you like, using GM over A. Take the square root. That's what I would choose to do. So I'm going to go ahead and do it that way and calculate the square root of G times the mass of 4 Vesta, 2.59 times 10 to the 20th power, divided by the orbital radius in units of meters, 510,500, enter. So the average orbital speed, which I didn't ask you for, is 184 meters per second. The periapsis velocity is this average speed times the square root of the ratio of the apoapsis radius divided by the periapsis radius. So I can't put off using the radius instead of the diameter anymore. I'm going to have to treat this as 263 plus 425 divided by 263 plus 70. Great. Here we go. This answer times the square root of, open parentheses, 263 plus 425, close parentheses, divide by, open parentheses, 263 plus 70, close parentheses, enter. I get 264 meters per second. Party. Well, part D, actually. Part D, calculate the apoapsis velocity. Well, if you do things just right, it's flipping the numerator and the denominator here. And that shows up on my handy dandy reference sheet as apoapsis velocity is the product of the average orbital speed times the square root of the periapsis radius over the apoapsis radius. So what I could do here on my calculator is recall the previous equation, replace answer with the average orbital speed, which was 184, and instead of multiplying, choosing to divide. Enter. Okay, well, you know, once you get proficient with math, you can do stuff like that quickly. I get an apple axis velocity of 128 meters per second. This ends problem 3. Of course, the homework title was circular, problems 1 and 2, elliptical, problem 3, and Hoffman, problem 4. Yes. A Dragon spacecraft is in a circular orbit around 4 Vesta. Its altitude is 75.0 kilometers above the mean surface of this asteroid. The crew decides to undergo Hoffman transfer to a circular orbit with an altitude of 315 kilometers above its mean surface. Calculate everything in the known universe that you can tell me about that situation from A through I. So this is a combination of 2 circular orbit problems, like problem 1 and problem 2, plus an elliptical orbit problem, like problem 3, with a sprinkling of a little bit more algebra afterwards. So parts F, G, H, and I are what's in addition to parts A through E. To do this, part A, it's a circular orbit. So you're going to use V equals the square root of GM over R. And what I'm going to do is just list all the formulas and then knock it out on my calculator in 2 seconds. For part B, you're going to again use V equals square root of GM over the outer orbit. So I'll put a little subscript O for I, outer, a little subscript I for inner, in very small font that is not focused. Part C, the transfer orbit average velocity. So first, you need to calculate the semi-major axis. And then, right, so A equals R inner plus R outer divided by 2. And, by the way, this inner radius is the radius of 4 Vesta plus the periapsis altitude. The outer orbit radius is the radius of Vesta plus the apoapsis altitude. After you get the semi-major axis, why then you could just do average velocity is square root of gm over a, the semi-major axis. Part D, the transfer orbit periapsis velocity. The periapsis velocity is the average velocity times the square root of the apoapsis radius divided by the periapsis radius. Transfer orbit apoapsis velocity. The apoapsis velocity is the product of the average orbital velocity either divided by that or times the square root of the periapsis radius divided by the apoapsis radius. Part F. Here's the new part. So my handy dandy crude sketch here is supposed to enlighten you. Here's the inner circular orbit, not the asteroid. Here's the outer circular orbit, not anything else. See, labeled inner orbit, boop, outer orbit. Boom. The transfer orbit is the ellipse that just touches the inner orbit and the outer orbit at one point. The delta V to escape the circular orbit is the difference in speed between the circular orbit, in other words, your answer to part A, and the periapsis speed, in other words, your answer to part D. So not algebraically, but in terms of which part of the problem we're doing, the answer to part F is equal to the answer to part D minus the answer to part A. That gets you going uphill from the Earth, slowing down, slowing down. Now you're going too slow when you get to the outer orbit. The delta V to speed up onto the outer circular orbit is the difference between your answer to part B and your answer to part E. The total delta V, part H, is going to be your answer to part F plus your answer to part G. And then finally, the time of flight for the transfer maneuver, TOF we call this, is going to be half the orbital period of the elliptical orbit. So from inner to outer is half an orbit, from outer to inner is half an orbit. We want the orbital period of the elliptical orbit and then divide that by 2. And so that's something we didn't actually calculate as any of the parts. So you're going to have to go t squared equals 4 pi squared a cubed divided by g divided by m. And then time of flight is equal to the period of the elliptical orbit. I'll put subscript a divided by 2. All right. And finally, here are all the answers. I'm just going to use my handy dandy program to knock them all out at once. First, this is not the Earth, the Moon, Mars, the Sun. So, other. The mass of 4 Vesta is 2.59 times 10 to the 20th power. And I am distracted, so let's just put in 5 and quit. And I'll see you after your break. Okay, welcome back from break. We're now going to put the answers into a program or run a program that will give us the answers. So, program, orbit, central body is not the Earth, the Moon, Mars, the Sun. So, other. Its mass is the mass of Vesta, which is 2.59 times 10 to the 20th power. Now, the radius wasn't given directly. Instead, the diameter was 526. So if I put in 526, that will be wrong. But if I divide that by 2, that will be the radius. Ta-da! And now, might as well do just problem 4. So we're going to do a Hoffman transfer. And the input will be 2 radii, because I never wrote anything else. For the first radius, it's going to be the radius of the planet plus 75 kilometers. For the apoapsis radius, it's going to be the radius of the planet plus 315 kilometers. Boop. Here are all the answers. The inner orbit velocity is 30 meters per second. The outer orbit velocity is 173 meters per second. The transfer orbit average orbital velocity is 41 meters per second. The transfer orbit periapsis velocity is flawed. There are clearly mistakes on all of these answers. Okay, so either I have a programming error or I put the wrong numbers into the calculator. So I'm going to just start all over and first put in the mass of 4 Vesta as 2.59 times 10 to the 20th power. Boop. The radius in kilometers should be 526 divided by 2. To do a Hoffman transfer with 2 radii, it should be alpha b plus 75. The apoapsis radius should be alpha b plus 315. Okay, so I typed in an incorrect value earlier because I have faith that I've debugged my program and have the program should be working correctly. So for the program, it says the inner orbit velocity is 226 meters per second. The outer orbit velocity is 173 meters per second. The transfer orbit average velocity is 194 meters per second. The transfer orbit periapsis velocity is 254 meters per second. Part E, the apoapsis velocity is 149 meters per second. Part F, the delta V to depart the inner orbit is 28 meters per second. Part G, the delta V to enter the outer orbit is 24 meters per second. Part H, the total delta V is 52 meters per second. Part I, the total time of flight is 7,407 seconds. Boop. Piece of cake. And by the way, 7407 divided by 60 means 123 minutes. Okay, so that is using your pen and paper and calculator to do this homework assignment. Now, I'm going to show you a second way to do this homework assignment.